something, and I'm going to read this out to you now from the specification because it's a little bit different to the others. Here's what it says. Students should recognise the use of the small angle approximation in the derivation of the time period for examples of approximate SHM. So it's not about you memorising a particular derivation, it's about you recognising a mathematical technique being used, the small angle approximation. What is the small angle approximation? Are you ready for this? Second board, didn't expect that, did you? This is the small angle approximation. Again, the thing that you really need isn't all the bump around it, you just need to know, vitally need to know, that the sine theta is approximately equal to theta. That's the small angle approximation. Sine theta is also approximately equal to s over a, where s is this curved bit and a is this not curved bit, the adjacent, if you're going to be a little bit more technical. So in the rest of the video we'll just explain why this is the case, why we can be confident in saying that sine theta is pretty much theta and is pretty much s over a when theta is small, and we're also going to be looking at how it can be used. So let's start with this then. So what we've got here is a triangle. Hopefully you recognise that, otherwise there is a problem. We've got hypotenuse here, opposite and adjacent of course, and sine theta is defined as opposite over hypotenuse. But if theta is kind of small, which it is in my example, in the book they go for sort of theta being about sort of 10 degrees or less to give you an idea of what small is. If theta is kind of 10 degrees or less, it's pretty small, then opposite over hypotenuse is pretty much going to be the same as opposite over adjacent, because this length and this length are going to be pretty close. As theta gets smaller, h and a are going to get closer and closer together in terms of their value. So O over h is pretty much the same as O over a, kind of ish. And then you'll also notice here that what we've got is inside the triangle I've made a bit of a curved line there. I've made the arc of a circle, essentially. That's what that S is. So that if I ignored this bit here, if I just measured from this end of this curved line here to that, that would be exactly the length of A. Both of those would form the radius of the circle, of which S is a small arc. So with that we can say that O is pretty much going to be the same length as S when theta is small again. So O is pretty much the same size as S, so O over H is about the same size as S over A. So if you take the curved length of this arc and divide it by the length of this adjacent line here, it's pretty much the same as sine theta. Now we can go one better than that. We can actually have a look at what this S over A actually is, because there's an expression for how big that arc length is going to be. As you can see here, we can, instead of saying the arc length, we can say A times theta. The reason for that, if you haven't done arc length before, is because the arc length is a fraction of the whole circle. So if we want to know how long the arc length is going to be, we take the length of the whole circle, which would be 2 pi r, and seeing as the radius is going to be a, let's just call it 2 pi a. And then we'd need to take whatever fraction of the circle we've got, multiply that fraction by 2 pi a, and we'll end up with s, because we want to know what fraction of the whole circle s is. The fraction of the circle that we've got is going to be theta over 2 pi radians. So we've got theta over 2 pi, times that by 2 pi a, we find that the arc length of an arc is going to be equal to the angle theta times the radius, which in this case is a. So instead of saying s, we can say a theta, so this becomes a theta over a, which of course is just theta. So sine theta is going to be approximately equal to theta for small values of theta. That's the small angle approximation. So sine theta is approximately equal to theta. It's also approximately equal to the curved arc length divided by the radius. There are other ways of proving that as well. Taylor series expansion you can use, but we're not going to get into that. If you feel like having a bit of fun on the internet, you can have a look, and it goes into great detail as to how that all works. It's very interesting. We don't have time. So that's the small angle approximation. How is it actually useful? Well, let's go back to the actual board for today, which is here. There it is. This derivation here uses the small angle approximation. You might be able to spot it at the bottom there. We'll go over why that is. Just before I do though, it does say in the spec that you need to know or be able to recognise when it's being used to derive the time period. And you'll notice we haven't done that in this. That's because the book doesn't derive the time period for SHM by using a small angle approximation. You'll still be able to recognise this technique, and you'll still be able to use this to work out the time period, because the acceleration is equal to minus brackets 2 pi f close brackets squared x, and we know that f is 1 over t, so you can work out the time period from the acceleration from that. But that's more maths we don't necessarily need to do. It's all about recognising where that small angle approximation is. There it is. For theta smaller than 10 degrees, we can pretty much say that sine theta is equal to s over L. You will recognise that because s over L is that curve length divided by the radius there, which, if we go back to the first board, you will see there. That was that s over a thing that you can see. There we go. So finally, and you don't need to watch this if you're happy with where this derivation comes from, but in the last part we're just going to have a look at where the derivation comes from. So here's my pendulum. You could do the same sort of thing if you wanted to for any other object in SHM, but we're going to do it with the pendulum. Pendulum's got a length L, it's got a curved length that it's travelling with S, and at the moment it's at an angle theta to the vertical line there. If we look at the forces, which is going to be important if we want to work out the acceleration, we find that there's a big tension force pulling it upwards on that string there, and then the only other force really that's acting is weight, mg. The weight's going to have two components, one of which we're really interested in and one of which we have no interest in at all. The weight component here, and most of the weight component, is going into stretching the string here. It's going to be the same size incidentally as the tension force, although it's not clear from the diagram that that's the case. And that's going to be the component of the weight. The weight, remember, is vertically downwards. You know how weight works. The component of the weight that's along the line of the string is going to be mg times cos theta, because it's adjacent to the theta. The one that we're really interested in is the restoring force, the one that's trying to push it in towards the centre. That's going to be the one that's at 90 degrees to the string, and it's going to be mg sine theta. You'll notice that when I write the restoring force, I put a negative sign in. That's because it's acting towards the negative. It's a restoring force. So the force here is minus mg sine theta. Now if we want to know the acceleration, which we dearly do, we're going to use Newton's second law for that. A is F over m. So we just take this expression for the force and divide it by the mass. So that simplifies down to minus g sine theta, which is lovely, but we can make it even better than that because we're noticing that we've got this sine theta term here. We could just call it theta, but that would be a bit of a pain because we'd have to measure what theta was, and that's a little bit tricky sometimes. So a lot of the time it's a lot easier to, instead of approximating sine theta for theta, let's approximate it to s over L, that curve length divided by that long length that we saw from before. And all of that then becomes that, and you end up with A is minus g over L s. And that is how that works. Video 3 is done.